All right, let's get into it. Today, we're going to architect one of the most critical pieces of any large-scale system, the rate limiter. Exactly. And we're not just talking theory here. We're going to build this thing from the ground up, focusing on the real-world trade-offs you have to make to handle millions of requests with basically zero performance hit. We're aiming for sub-millisecond overhead.
So, at its core, what is a rate limiter? It's a defensive mechanism. You see it here as a shield, which is honestly the perfect analogy. It's all about protecting your backend services from getting totally overwhelmed, right? And that could be from a sudden legit traffic spike or, a malicious denial of service attack. It's about keeping things stable and making sure everyone gets fair access to resources.
And that right there is the fundamental engineering challenge, isn't it? We're building this shield, but the shield itself can't slow down the very army it's supposed to be protecting. Absolutely. You have to enforce all these traffic limits without killing your non-functional requirements. The system needs to be highly available, it needs to be scalable, and most importantly, it has to have incredibly low latency. Because remember, every single request is going to pass through this.
Okay, so first things first. Let's start with our first major decision, defining the actual throttling policies. And this is way more complex than just picking a number out of thin air. It's really about defining how the system behaves when that limit is approached or, even blown past.
So looking at the slide, we've got three main strategies. Hard throttling is the most straightforward. You hit the limit, bam, you're cut off. Done. Soft throttling gives you a little bit of a grace period, right? A small percentage of burst capacity. But the one that's really interesting here is elastic throttling. This is a much more dynamic, a much smarter approach. It basically says, hey, if the backend services have spare CPU and memory just sitting there, let's allow a temporary burst. It intelligently uses that excess capacity instead of just letting it go to waste.
All right, so we've got our policy figured out. Now we move on to the next big architectural choice, and it is a big one. Where does this rate limiter actually live inside our infrastructure stack?
Well, we could put it on the client side, but that's a complete non-starter from a security perspective. Oh, for sure. Any malicious actor could just disable it or tamper with it, and it's useless. So, okay, what about putting it directly on each API server? Well, that's better, but then you end up with all this decentralized logic, and you could have inconsistencies between servers.
So that leads us to what is really the optimal solution, a dedicated, stateless middleware service, exactly. By placing it right at the entry point to our API gateway, we get this one centralized, authoritative vantage point. We can control all incoming traffic before it ever even touches our core application servers. It's way more secure and just a lot easier to manage.
And now we get to the real heart of the performance challenge. In a distributed system that's handling thousands of requests a second, how do we manage state? Specifically, how do we manage the request counters without creating a massive, system-wide bottleneck? This is where it gets really, really tricky.
This is the classic concurrency problem, right? What happens if a bunch of threads or processes for the exact same user hit our rate limiter at the exact same instant? You're just asking for race conditions that could completely undermine the very limits we're trying to enforce. The entire system could fail at its one job.
This slide breaks down that get-then-set failure just perfectly. So look at the flow. Request 1 comes in, thread A reads the current count. Let's say it's 99. But before it can write the new value, request 2 for the same user hits. Thread B times also reads the count, and what does it see? It also sees 99. Right. Then they both increment their local value to 100 and write it back. And what's the result? We've processed 2 requests, but only incremented the counter by 1. The rate limit has just been bypassed.
The naive solution here is to just throw a lock on it. But as the slide says, that is a performance disaster at scale. It just serializes all your updates and creates massive lock contention. The real engineering solutions are way more sophisticated. We can use atomic operations like the NCR command in Redis that's a set-then-get pattern that just avoids the race condition completely. Or, for even bigger scale, you can use sharded counters to distribute that write load across multiple keys, which is absolutely crucial for reducing write contention.
Okay, so with those core challenges now solved, let's start actually architecting the service and its components. This is the blueprint. Let's lay out all the building blocks for this thing.
So we have 4 key building blocks. First, the rule database. That's our persistent source of truth. But for performance, we absolutely have to have a throttle rules cache. Probably something like Redis for those sub-millisecond lookups. Then you have the decision maker. That's the brain of the operation with all the core logic. And finally, you'll need a queue if you're using those soft or elastic throttling policies we talked about, to buffer requests.
And that decision maker isn't just some simple counter. It's a full-on engine that can implement all sorts of sophisticated algorithms, right? Depending on the use case, we might need a token bucket, or a leaking bucket, or different kinds of sliding window counters. It has to be flexible enough to enforce our rules accurately.
All right, now for the final, and I think the most advanced optimization we can make. We've solved for concurrency, but how do we absolutely crush the latency this service adds to every single API call? This is all about optimizing the critical path.
So the standard approach is synchronous. A request comes in, we read from the cache, we increment the value, and then we write it back to the cache. And only after all that do we respond to the client. That round trip to the cache, especially that write operation, is sitting directly on the client's critical path. At scale, that latency adds up fast and becomes a major problem. So the key insight here, the big idea, is this. We can decouple the decision from that expensive write operation. We make the decision based on the data we have in front of us right now, and then we handle the update asynchronously, taking it completely off the client's critical path.
And this slide illustrates that two-phase approach brilliantly. Phase 1 is online. This is the fast part. We do a quick low-latency read from the cache and immediately tell the client, yes, you're good, or no, you're not. Then comes Phase 2, which is offline. After we've already responded to the client, we fire off an asynchronous job to increment the counter. The client gets its response way faster, and the system eventually catches up on the backend.
And the impact of this is just massive. For a handful of requests, you wouldn't even notice. But when you're handling millions of concurrent API calls, moving that write operation offline shaves critical milliseconds off every single request. That adds up to a huge increase in overall system performance and throughput. It's a game changer.
So, we've designed this powerful, super performance system. But let's end with one final and really tough engineering question. What happens when your Redis cache goes down? Do you fail open and just let all the traffic through, potentially overloading your backend services? Or do you fail closed, denying all traffic and effectively taking your entire API offline? There's no single right answer here, and what you choose really reveals the true priorities of your system. Definitely something to think about.